Now we see the invariance properties. The contributive properties invariant by similarity transformations. Consider you have the system xk plus 1 jxk plus huk and you have the x bar k plus 1 equal to g bar x bar k plus h u and u k the same inputs. I can say that where the state variable about the is have a is equal to p x bar, and easily you can define the j bar equal to p minus g p, because if you substitute here you can find the x bar over the k plus 1 equal to g bar x k is equal to p x bar k plus h u k, and here equal to p x bar and x k plus 1 equal to p inverse of the gp, and here become p inverse about the h. That means x bar k plus 1 will be p minus 1 p inverse gp, and I can say this is g bar, and h bar equal to p inverse about the multiply h become the h bar. If the system k is controllable, then you can see that this system will be controllable too. And it's obvious because C, the matrix about the C is equal to P minus 1 C. And if C is a complete rank, the C bar will be this is C bar. I can C bar equal to P minus 1 C, and the both rank will be the same as each others, and they will become controllable. Exactly, we can say in the continuous time x dot t equal to a x t plus b u t, and the matrix of the 6 or the system of the 6 is controllable if only if the rank of the controllability matrix is equal to the dimension about the system. Here is a matrix about the a, here is a b, in the discrete time is a g and the h, and the matrix of the c it was h and g h, here become b a b etc, and the rank of the c is equal to rank about this matrix and should be equal to the dimension about the system. Now we will see the pole place method, how they can solve the find the matrix or the find about the k. If my matrix or my system is controllable, with the pole placement method you can find the k. Okay, necessary and sufficient condition for pole placement, the system F7 is a state controllable. It is possible to find the k in order to place arbitrarily all pole of the system within feedback UA k. And if you remember, the UA feedback equal to minus kx k, or you can say the UA k equal to kx k if your feedback is positive. Now UA k equal to minus kx k, then the closed loop pole system becomes something like this. If you substitute the UA k here by the minus k x k and the factor is about the x k, you can find the j minus h k x k. Okay, the x k is equal to j minus h k. Pole place method is a pole of the system is equal to pole of the closed loop transfer function in a single input, single output. But pole of the system for the multiple input multi-output is equal to eigenvalue of the closed loop system. If you remember, the closed loop system is equal to zi minus g minus hk, and this is equal to determination about the zi minus j minus hk is equal to the 0. Assuming that we want to place the pole in the P1, P2 and Pn, how we can choose the k to have this? How you can find the k that if you see the system is g minus h k, how you can find this one? That means the determination about here is equal to my desire about my pole. They have a different method, the direct computation of the k by identifications. The MATLAB's functions, the k is a place of the gh by my pole, desire my pole. Normally we use this method. Or the MATLAB is a k equal to occur the gh this for the eigenvalue for the same multiplicity ordered by the single input and the single output system. Okay, now we give the one example. Consider that you have this system, the g is equal to here and h equal to here. Find the gain of the k to have the two pole in one of them 0.5 plus j 0.5, one of them here, another one is here. This is the two pole I have, and if you remember, this one is a 0.5 is a I want these two pole, I have these two pole, I find a k. This two pole is my desire. You can select any pole that your system becomes stable. Define the k. For finding the k is easy. You can say the system first is a controllable when uak equal to minus kxk, then xk plus 1 equal to j minus h kxk. My system changed to this, my state feedback system. Now I must find the 2k, k1 and k2, zi minus j plus hk equal to z2 plus k2z minus 2 plus k2. I would like to solve this one. If you remember, the j for me is this 0 1 1 0 and h is 1 0. Here they ask me the zi. That means zi for me, this one becomes z minus 1, here becomes 0, this one becomes 0, this one becomes z minus 1 minus j. J for me it was 0 1 0 1 and 1 0 plus h is 0 1 and k equal to k1 and k2. If you find here determination about the all here, you find z2 plus k2 z minus 2 plus k1, and I want to equal to two pole z minus p1 z minus p2, and I know about the p1 and p2. If a multiplication becomes z2 minus z plus 0.5, these two equations should be equal together. This z2 is equal to 1 by 1, and this k2 equal to minus 1, and the k1 plus minus 2 equal to 0.5. You can find the k1 equal to k2 equal to. That means with this state variable, with this k, with the state variable about my system, your system can reach to these two pole, or that my system with this k I can find these two pole. Okay, now we extended this system. If you remember the canonical control system, is all the, here is a 0, here is a minus an minus 1 minus a minus 2, and the k is the dimension about the k minus n until k 1. I want to see how can I find the k. The first of all, I find the determination zi minus j plus hak, and this determination you will find as zn plus a1 plus k1 zn minus 1, and if you continue you will find the kn. This is a determination about this matrix. And now you have the compute for the n equal to 3. You will see here become a3 plus k3, a2 plus k2, and here will be a1 plus k1. And if you find the determination about this system, you can find as z3, a1 plus k1 z2, a2 plus k2 z plus a3 plus k3. This equal to my desire about the pole. I have a 3, you can have a 3 desire pole. Here my desired pole, I put z minus p1, z minus p2, z minus pn, and if you extend that, you have the zn, you have a coefficient about the mu zn minus 1, etc. If you these two equations equal together, you can find the k. K will be mu n minus an until you mu 1 minus a1. And this one, if the system is not original in the controllable canonical form, but there exists a chance, a basic matrix of the P such that we can turn the original system into the controllable system. If you remember, x equal to x bar equal to px, you can find the sum p to change the original system into the controllable system. Then the k will be k dot p inverse. Now we give the sum example. First of all, find the gain of the k to have the 1, 2, 3 pole, because your matrix is a 3 by 3, you have a 3 pole. Of the closed loop, you have two method. One method you can find the zi minus j hk and find the determination equal to z plus 0.5 and multiply z minus 0.5 and the z, and these two equations equal together, you can find the k1, k2 and k3, or you can put the in the formula you define the a3 is equal to minus 2, a2 equal to minus 1, and a1 is 3. Since they have a 3 pole, z minus 0.5, z plus 0.5, and z equal to the 0. These two equations equal together, you can find the k1, k2. Or you can find the mu here 1 is 0, because here is z2 we don't have. Mu 2 equal to minus 0.25 and mu 3 equal to 0. Then k equal to mu 3 minus a3, mu 2 minus a2, mu 1 minus a1. You can find the k1, k2 and the k3, or you can find the matrix about the k.